I'm Gary Pocock, and this is my week 14 reflection for the modelling instruction course. This week I'm going to talk about two concepts that came up in our discussion of magnetism, and that they are the concepts of EMF and magnetic flux, two concepts that are known to cause problems. Alright, so starting off, talking about EMF. Now, I know in the modelling instruction course this concept was avoided when we were talking about circuits, but it came up when we talked about motional EMF. So I thought I'd go right back to the beginning and just delve into this concept of EMF. So what I did a little bit of a search, and I found this paper from 1979, which talks about the concept in some detail and goes into a little bit of the historical background of it. And I found it quite interesting because I could see links between the discussion in this paper and modern textbook discussions, which I'll illustrate shortly. Okay, so here's the paper. Okay, so Volta's forgotten concept, electromotive force, and they start off by commenting that Volta himself coined the term electromotive force, and he defined it as follows: a non-electrostatic action on charges in conductors that cause unlike charges to separate and remain separated. Okay, so this is good reasoning, and I think it's quite clear what's going on here. So we're saying, look, these charges that want to attract one another, well, they are attracting one another electrostatically, and yet somehow they are being pushed apart. So Volta hypothesizes that there is some other kind of force, non-electrostatic, that is pushing them apart. As we know, this concept has been significantly modified. The modern concept of EMF drops the idea of it being a force and focuses on energy per unit charge in its definition. The modern concept also has to get rid of the idea that charges are necessarily separated, because when we come to EM induction, if we look at a metallic ring, then we are able to get current flowing in a metallic ring without a charge separation, without a potential difference occurring. So that bit has to go as well. The thing that remains from Volta's original definition, as we'll see in a second, is this idea of a non-electrostatic action. Right, so the author of the 79 paper, authors Varney and Fisher, they propose this definition of EMF. Now, this is not original to them, although the way they present it, I think, might be. They refer back, believe it or not, to a textbook from 1904, a textbook Abraham, 1904, but they also note that this concept was used by Panofsky in the 1955 textbook, and that's going back a long way, but I checked out the Panofsky textbook, and that is still widely used, widely recommended in university electromagnetism courses. So here's their idea. Paralleling the definition of potential difference, they define EMF as the path integral of this hypothesized non-electrostatic magnetic field. Right, so this is a model that they're producing. So they're under no illusions that there is a real field like this. So in fact, they'll actually say, look, in the context of batteries, this E' field is a heuristic one, which I guess nowadays we would say this is just a model for what's going on inside the battery. So, comments on this definition. Firstly, it's plus sign rather than a negative sign because this is work done per unit charge. The integral is path dependent, unlike the integral for potential difference. And again, that makes sense. This is a non-conservative force, like a friction force. So that's their idea. And to me, it made a lot of sense. And I was able to get a clearer distinction between EMF and potential difference. So EMF is the work done by a non-electrostatic field. It could be a magnetic field. It could be a friction field, as in when we're rubbing rods and creating static electricity. Whatever it is, it's creating a separation of charge. And the article notes the widespread confusion about EMF. And this is just an example of that confusion. This comes from the Hyperphysics website, which is a good website. And he's got this little flow chart here, which has many useful things in it. But right at the top, he's got this EMF is voltage. And that is just such a widespread confusion. Okay, the paper also comments that in traditional presentations of EMF or traditional presentations of electrostatics, we discuss the electrostatic force at length, but we don't focus on the fact that it requires a non-electrostatic action to actually separate these charges in the first place. And no doubt that's why there is such confusion about the concept of EMF. Alright, so turning to more modern textbooks, you can see this is Randall Knight's textbook, and you can see in this summary paragraph, this bit occurs at the beginning of the chapter. He says, we'll learn that any non-electrical means of separating charge is what we call EMF. And clearly that is referring back to the work of that 1979 paper or previous work where this concept is being developed. And this is Knight's mechanical conveyor belt model of a battery. Chabet and Sherwood use a similar idea. I think they refer to non-coulombic forces, non-coulombic fields. Same idea. Alright, now this is a little diagram I came up with inspired by Knight's diagram, but also inspired by this paper here, which I also came across, which is called Voltaic Cells for Physicists, in which they make the comment in the first paragraph about how the peculiar situation is that physics, we focus on the voltage aspects of batteries, while in chemistry we focus on the chemical energy aspects of batteries. And there's nowhere that these two things are really put together to give a complete picture. And that struck me as very true even within my own brain, because then I came down and read this, and it says, as is well known to electrochemists, inside the battery there are actually two step-like voltage jumps, one at each electrode-electrolyte interface, and the internal resistance is associated with the electrolyte between the electrodes. And when I read that, I said, well, yes, of course, my chemistry brain knows that that's true, but my physics brain hadn't really connected that up. And I thought, looking inspired by Knight's little diagram here, we could modify it slightly and do it like this. So here I've got the battery on the side, and but vertically still representing increasing potential energy. So we can imagine our charge getting a potential energy jump in the vicinity of the first electrode, then travelling through the electrolyte, and then getting another jump in potential in the vicinity of the second electrode. And then the whole business of internal resistance, which I've always found difficult to explain, and avoided it if I can, is quite easily explained by just viewing what's happening through the electrolyte in the centre here. Here is where the internal resistance is happening, which I think is a lot clearer than the standard diagrams where you write out where they put a battery and then they put a little resistor outside the battery to represent internal resistance. Okay, so and the other thing I liked about Knight's book was that he used the phrase chemical EMF, and that juxtaposed nicely with the idea of emotional EMF when you're moving through a magnetic field. So here we've got work done chemically to separate the charges, and the work done per unit charge is the chemical EMF. So that little excursion of mine certainly clarified the concept of EMF in my brain. And to sum up, I thought, well, what would I be teaching the students? I certainly wouldn't be trying to teach the path integral definition. That helped me, but I wouldn't be trying to do that, obviously, in an introductory course. Nevertheless, I think I would try to make it much clearer what EMF is verbally by simply emphasizing that its work has to be done to overcome the electrostatic attraction, to keep and to separate the charges, and that work per unit charge is EMF. And there are a variety of non-electrostatic ways of doing that work. And the last comment I have in relation to this is a paper here. There are very few recent papers on EMF. Very few papers at all in physics education research on EMF. This paper is from 2013, or published 2014, and it's a survey of university students' understanding of electromotive force. And what they did was they asked their students 4 questions about this. Question 1. This was based on piezoelectric effect. And they graded these questions in terms of explanation. So they weren't just multiple choice. They asked the students to provide clear explanations. And then they carefully graded them. And the results, not surprisingly, or actually they're a bit surprising just how bad they are. So here are their results. This is up here. These are the 3 universities that were surveyed. Option A is the fully correct answer. So you see question 1, typically only 6% or 5% got a fully correct answer. Question 2, we're talking 8%, a little bit higher over here. Question 3, around the 10% mark. Question 4, around the 20% mark. So very, very poor understanding of EMF amongst university students. So it's something that clearly needs to be focused on a little bit more. Okay, I'm running out of time, so I'm not going to have much time to do magnetic flux. So very quickly I would say this is not a difficult concept, but it is often glided over too quickly in the notes, and I think that was the case in the modelling instruction notes. So I just had the thought of doing a quick worksheet on it, just really basic stuff like, what's the flux for all these different shapes, and then have changing magnetic fields and ask what the flux is in those shapes, and then move a wire through a field and get them to plot the change in flux. So a little bit more scaffolding for magnetic flux, I think, would solve a lot of the confusions.